This presentation deals with a few of the technical considerations associated with well construction and sample collection. Its purpose is to provide a general understanding of the equipment and procedures used in well construction and sample collection. It is not intended to make experts of those viewing it. Hollow stem auger drilling is currently a popular method of borehole construction, monitoring well installation, and sample collection in unconsolidated material. An auger section, commonly referred to as a flight, consists of a hollow length of pipe with continuous spiral flanges called flighting welded to the exterior. Auger flights used in well drilling are commonly 5 feet long, with outside diameters ranging from 6 to 22 inches and inside diameters ranging from 2.5 to 13 inches. Once the location of the well has been selected, the drilling rig is positioned on site and leveled. The rig is leveled by adjusting hydraulic jacks located in the front and back of the truck. Leveling ensures that a plumb or vertical hole will be drilled and minimizes the amount of tool drag and disturbance along the walls of the borehole. As the tower is hydraulically raised, all personnel should stand clear of the rig. Care must be taken to ensure that overhead power lines and other possible obstructions do not interfere with the tower. When in position, the tower is locked into place. When drilling with hollow stem augers, 2 tool strings are commonly used, the auger string and the solid rod string. The auger string consists of joined auger flights. The leading flight is equipped with a cutter head that extends beyond the flighting. The solid rod string, which lies inside the auger string, consists of joined sections of solid rod with a pilot bit at the end. Both tool strings, coupled at the spindle of the drill rig, rotate and advance at the same rate. As the auger is advanced, cuttings are brought to the surface by the flighting, which acts as a screw conveyor. The pilot bit keeps the annular area of the hollow stem auger free of cuttings. 5-foot sections of auger and rod are added to the tool strings as drilling proceeds. Once the desired borehole depth has been reached, the solid rod tool string is removed. As rod sections are decoupled at the surface, a fork tool is used to prevent the remaining string from slipping down the borehole. The auger tool string may be pulled or left in place as a temporary casing to prevent collapse of the borehole walls. This is particularly important in non-cohesive formations. Prior to setting the well casing into the borehole or the hollow auger flights, a bailer is used to remove the muddy water. The bailer consists of a length of pipe fitted with a foot valve at its base. The bailer is lowered into the borehole where it fills with water, and then it is lifted. Turbid water and sediment are dumped on the ground when the foot valve is depressed. Once the borehole has been cleaned by bailing, it is ready to receive the well screen and casing. With the auger flights in place, the well screen and casing are lowered through the auger's hollow center. Next, sand is poured into the annular space between the auger string and the well casing. The sand pack is built in 1 to 2 foot long vertical sections called lifts. At the completion of each lift, the auger string is pulled back to expose the sand pack and screen to the formation. This process continues until the sand pack extends at least a foot above the top of the well screen. Next, a 1 to 2 foot long seal pack is built above the sand pack. The seal is generally composed of a swelling material such as bentonite clay. The remainder of the borehole is then backfilled as the auger string is removed. Finally, the upper 5 to 20 feet of the annular space is filled with cement, and a concrete pad is constructed around the well. Their purpose is to form another seal to prevent water and other fluids from entering the well bore. New wells should be developed by pumping to achieve sediment-free water and maximum well yield. During well development, rapid changes in air or water pressure in the well force water to quickly flow into and out of the well screen and formation. This process removes most of the fine particles in the vicinity of the well, thus increasing the hydraulic conductivity around the screen. Continuous core samples can be taken with a thin wall sample tube attached to the solid rod string. The drive head, which connects the sample tube to the rod string, contains a ball valve that vents excessive air and fluid pressures generated during the coring process. The leading end of the sample tube has a cutting shoe that functions as a pilot bit and a core retainer basket that prevents the loss of unconsolidated samples. Both tool strings are coupled to a bearing that allows the sample tube to remain stationary when the auger is rotated. Drilling and coring occur simultaneously as both tool strings are advanced at the same rate. When full, the sample tube is retrieved with a wireline drum hoist. The drive head and cutting shoe are removed, and the core is extruded from the sample tube with a hydraulic piston. As coring continues, the cleaned, reassembled sample tube is lowered to the bottom of the bore hole, and 5-foot lengths of rod and auger are joined to the tool strings. One of the advantages of using a hollow stem auger is that coring can be conducted without using drilling fluids, which could alter the chemical and biological integrity of core samples. Another type of sampling device is the reciprocating hydraulic hammer, which minimizes core sample disturbance during collection. This method involves drilling with an auger and a solid rod string with a pilot bit. When the interval to be sampled has been reached, the solid rod string is retrieved. A thin-walled sample tube is attached to the leading rod, and the assembly is lowered down the borehole. The sample tube is driven into the formation by a reciprocating hydraulic hammer attached to the rod string. The construction of wells and the collection of samples in saturated non-cohesive heaving sands requires the use of specially designed equipment. One method is to use a clamshell cap. A clamshell cap fitted to the hollow stem auger bit keeps heaving material from invading the hollow stem of the auger until the sampling tool is in place. The cap, mounted on hinges welded to the auger head, is held closed by pressure as the auger is rotated and advanced. When the interval to be sampled has been reached, the top auger is uncoupled and a thin-walled sample tube fitted with a wireline attached piston is prepared for sampling. The piston, positioned at the bottom of the tube, is adjusted to ensure a proper seal between the piston washers and the sample tube wall. The sample tube is attached to the solid rod and lowered inside the auger until it rests on the closed clamshell. The wireline attached to the internal piston is kept slack so that the piston will not be pulled upward from its original position. The auger string is then lifted about 10 inches to open the clamshell doors, which places the sample tube directly on top of the material to be sampled. The slack is removed from the wireline attached to the piston and marked at a reference point. The sample tube is then driven to the desired depth by a reciprocating hydraulic hammer. The wireline holds the internal piston at its original position, creating a partial vacuum on the sample that helps retain the core during retrieval. The core is detached from material below the cutting shoe by rotating the sample tube about 180 degrees and then slowly lifting it a few inches. The piston is then pulled to the top of the sample tube, and the tube is slowly retrieved with the wireline. During geochemical and microbiological sampling, cores are commonly extruded into an aseptic and oxygen-free glove box to ensure the chemical integrity of the sample. The plexiglass glove box, which contains pre-sterilized sample containers and stainless steel core pairing tools, is purged with pressurized nitrogen gas. The sample tube is inserted into the self-closing iris diaphragm, and core is extruded into sample containers. The ability to collect and preserve unaltered samples in the field is an important part of many site investigations. Although the various approaches used in well construction and sample collection appear to be simple and straightforward, there are many sophisticated details that need to be addressed. These details are determined by the specific conditions of the drilling program. Consistency, care, and safety are always major considerations in any drilling program.